Welcome! In this session, we'll tackle the problem number 1035, titled Uncrossed Lines. This is an exciting dynamic programming challenge where we explore how to optimize connections between two arrays while ensuring no crossings. Let's dive in and break it down step by step. In this problem, we're tasked with finding the maximum number of uncrossed lines that can be drawn between two integer arrays, nums1 and nums2. Imagine writing the elements of nums1 and nums2 on two parallel horizontal lines. A connecting line can be drawn between an element in nums1 and an element in nums2 if, and only if, the two values are equal. However, there's an additional constraint: these lines cannot cross. The goal is to determine the maximum number of such valid, uncrossed lines that can be drawn. The input consists of the two arrays, where their lengths are limited to 500, and their elements are integers between 1 and 2000. The output is a single integer representing the maximum number of uncrossed lines possible. To understand this better, let's look at an example. Suppose nums1 is 1, 4, 2, and nums2 is 1, 2, 4. The maximum number of uncrossed lines we can draw here is 2. Here's why: we can connect the one at nums1, 0, to the one at nums2, 0, and we can also connect the 2 at nums1, 2, to the 2 at nums2, 1. These two lines do not intersect. However, we cannot connect the 4 at nums1, 1, to the 4 at nums2, 2, without crossing one of the existing lines. Thus, the output is 2. Now, consider another example. Let nums1 be 2, 5, 1, 2, 5, and nums2 be 10, 5, 2, 1, 5, 2. Here, the maximum number of uncrossed lines is 3. We can connect the 5 at nums1, 1, to the 5 at nums2, 1, the 1 at nums1, 2, to the 1 at nums2, 3, and the 5 at nums1, 4, to the 5 at nums2, 4. While there are other potential connections, any additional lines would result in crossing. Therefore, the maximum number of uncrossed lines remains 3. Let's look at one more example. If nums1 is 1, 3, 7, 1, 7, 5, and nums2 is 1, 9, 2, 5, 1, the output is 2. In this case, we can connect the 1 at nums1, 0, to the 1 at nums2, 0, and the 5 at nums1, 5, to the 5 at nums2, 3. These two lines are uncrossed, and no additional connections can be made without causing intersections. This makes the maximum number of uncrossed lines equal to 2. Finally, let's go over the constraints and edge cases. Both nums1 and nums2 can have lengths between 1 and 500, and their elements range from 1 to 2000. For edge cases, if either array contains only one element, the output is 1 if their single elements are equal, otherwise, it's 0. If the two arrays have no common elements, the output is always 0 since no connections are possible. Additionally, the solution must handle large inputs efficiently, even when both arrays have lengths close to the maximum limit of 500. To tackle the uncrossed lines problem, we can start by considering different approaches. The brute force method involves generating all possible subsets of connections between elements in the two arrays, nums1 and nums2. We then check which subset has the maximum number of connections that do not cross. While this method ensures we find the solution, it requires exploring all possible combinations of pairs. With n and m being the lengths of nums1 and nums2, this results in an exponential time complexity of O(2) n plus m, which is impractical for larger inputs. Instead, we turn to an optimized approach based on dynamic programming. This technique is inspired by the longest common subsequence problem, where we break the problem into overlapping subproblems and store intermediate results to avoid redundant computations. Key observations include that if two elements match, we can connect them to increase the count, while mismatches give us a choice: either skip an element in one array or the other, taking the maximum result. By systematically iterating through the arrays and storing results in a 2D table, we can significantly improve efficiency and solve the problem in a structured way. To build on this dynamic programming approach, we define dp I(j) as the maximum number of uncrossed lines that can be formed using the first I elements of nums1 and the first j elements of nums2. The recurrence relation is straightforward: if nums1, I1, equals nums2, j1, we can connect these elements, so dp I(j) becomes dp I1, j1, plus 1. If they do not match, we have two options: either skip the current element in nums1 or skip the current element in nums2. In this case, dp I, j is the maximum of dp I1, j and dp I, j1. The base cases handle scenarios where one of the arrays is empty. If nums1 is empty, no lines can be formed, so dp 0, j is 0 for all j. Similarly, if nums2 is empty, dp I, 0 is 0 for all I. This approach ensures that we systematically compute the solution for all subproblems. The time complexity of this method is O and *m, because we fill an n by m table, with each entry taking constant time to compute. This dynamic programming approach has a space complexity of O and *m, due to the 2D table used to store intermediate results. However, we can optimize the space complexity to O, min, n, m, by using a rolling array, which only stores the results of the previous row. This reduces memory usage significantly while maintaining the correctness of the algorithm. Among the possible strategies, the dynamic programming approach stands out as the most efficient and reliable. It reduces the time complexity from exponential to polynomial, making it suitable for larger inputs. Unlike greedy methods, which might make locally optimal choices that fail to achieve a global optimum, dynamic programming explores all possibilities in a manageable way to ensure the best solution. Additionally, we considered the trade-offs between the 2D DP table and the space-optimized version. While the space-optimized version saves memory, it is slightly more complex to implement. Nevertheless, for very large inputs, it can be a practical choice. Overall, the dynamic programming approach balances simplicity, efficiency, and scalability. In conclusion, the dynamic programming strategy, with the option for space optimization, provides a clear, efficient, and scalable solution to the uncrossed lines problem. It avoids the computational infeasibility of brute force and the pitfalls of greedy methods, ensuring that we achieve the global optimum in a structured and manageable way. This makes it the ideal approach for solving this problem, especially when working with larger input sizes. In this problem, we are tasked with finding the maximum number of non-crossing connections between two arrays, nums1 and nums2. A connection is valid if the elements being connected are equal and the order of indices in both arrays is preserved, ensuring that no connections overlap. This problem is a variation of the longest common subsequence, or LCS, where instead of just finding a subsequence, we establish connections between matching elements while maintaining their relative order. To solve this, we define a dynamic programming state. Specifically, let dp I, j represent the maximum number of connections that can be formed using the first I elements of nums1 and the first j elements of nums2. For the base case, if either I equals 0 or j equals 0, the result is 0 because no connections are possible when one of the arrays is empty. The transition relation depends on whether the current elements from nums1 and nums2 match. If they do, we can form a connection and add 1 to the result of the subproblem that excludes these elements, represented as dp I1, j1, plus 1. If the elements at the current indices do not match, we cannot form a connection. In this case, the result will depend on the maximum value obtained by either excluding the current element of nums1 or excluding the current element of nums2. This can be expressed as taking the maximum of dp I1, j, and dp I, j1. By combining these two cases, we establish a general transition relation where dp I, j is equal to either dp I1, j1, plus 1 if there is a match, or the maximum of dp I1, j, and dp I, j1 if there is no match. With this relation defined, we can now iteratively compute the values in the dp table. Using a nested loop structure, we iterate through all possible indices I and j to fill the table step by step. The outer loop iterates through the elements of nums1, and for each index I, the inner loop iterates through the elements of nums2. At each step, we calculate dp I, j, based on the transition relation previously discussed. This approach ensures that all possible subproblems are solved, culminating in the final solution. The time complexity of this algorithm is O and *m, where n and m are the lengths of nums1 and nums2, respectively, since every cell in the dp table is computed exactly once. Similarly, the space complexity is also O and *m, due to the size of the dp table. Once the table is fully populated, the value at dp n m represents the maximum number of non-crossing connections between nums1 and nums2. It's worth noting that this problem is equivalent to finding the longest common subsequence, or LCS, between nums1 and nums2, with the order constraints naturally enforced by the dynamic programming table. To implement this solution, we use a 2D DP table with dimensions n+1 by m+1, where n and m are the lengths of nums1 and nums2. This table stores the intermediate results for all subproblems. However, to optimize space usage, we can reduce the DP table to a 2-row array, where one row represents the current state and the other represents the previous state. This optimization is possible because each state only depends on the values from the previous row. Additionally, we must handle edge cases to ensure the algorithm works under all scenarios. For example, if either nums1 or nums2 is empty, the result is 0 because no connections are possible. If there are no matches between the two arrays, the result is also 0. On the other hand, if the two arrays are identical, the result is simply the length of the array. Furthermore, the algorithm handles duplicate elements by relying on indices to enforce the order of connections. Let's now look at the pseudocode that ties all these concepts together. We start by defining a function max non-crossing connections that takes nums1 and nums2 as inputs. The lengths of the two arrays are calculated as n and m, and a DP table of size n+1 by m+1 is initialized with all entries set to 0. Using two nested loops, we fill the DP table by iterating through each index pair I and j. If the elements at nums1, I1, and nums2, j1 match, we update DP I, j to DP I1, j1 plus 1. Otherwise, DP I, j is set to the maximum of DP I1, j, and DP I, j1. After completing the table, the result is stored in DP n, m, which is returned as the output. This completes the implementation of the algorithm, providing an efficient solution to the problem of finding the maximum number of non-crossing connections. This implementation solves the uncrossed lines problem using a dynamic programming (DP) approach. The problem is a variation of the longest common subsequence (LCS) problem. Here's how the solution works. 1. We initialize two variables m and n to store the lengths of the input arrays nums1 and nums2, respectively. 2. A 2D DP table DP is created with dimensions m+1 in x, n+1, where DP I, j represents the maximum number of uncrossed lines that can be formed between the first I elements of nums1 and the first j elements of nums2. The table is initialized to zeros. 3. The core of the solution involves iterating through all pairs of indices I and j using nested loops. For each pair, if nums1, I1, equals nums2, j1, it means the current elements from both arrays can be connected. In this case, we extend the previous result by adding 1 to DP, I1, j1. Otherwise, we skip one of the elements, either from nums1 or nums2, and take the maximum value of DP, I1, j, or DP, I, j1. For the final result, which is the maximum number of uncrossed lines, is stored in DP, m, n, the bottom right cell of the DP table. This approach ensures that all possible connections are considered while maintaining the non-crossing condition. The time complexity is O, m*n, where m and n are the lengths of nums1 and nums2, making it efficient for the given problem constraints. This is the Java implementation for LeetCode problem number 1035, uncrossed lines. The logic mirrors the Python implementation, using a 2D dynamic programming table to compute the maximum number of uncrossed lines between two arrays. Key differences include explicit type declarations, the use of Java's math.max4 comparisons, and class structure adhering to Java conventions. To solve the problem of finding the maximum number of uncrossed lines between two arrays, we start by initializing some variables. Here, nums1 has a length of 3 and nums2 also has a length of 3, so we set m and n to 3 respectively. Next, we construct a two-dimensional dynamic programming table, or DP table, with dimensions m+1 by n+1, filling it initially with zeros. This table allows us to keep track of the maximum number of uncrossed lines we can achieve up to each pair of indices in nums1 and nums2. For the first step of filling this table, we start with I equal to 1 and j equal to 1. Since nums1, 0, equals nums2, 0, which is 1, we update DP, 1, 1, to be DP, 0, 0, plus 1, resulting in a value of 1. At this point, the DP table reflects this update, showing a 1 in the DP, 1, 1, position while all other values remain 0. Next, we move to the following positions in the DP table. For I equal to 1 and j equal to 2, nums 1, 0, does not match nums 2, 1, as 1 is not equal to 2. In this case, we use the formula max, dp, 0, 2, dp, 1, 1, which results in dp, 1, 2, remaining 1. Similarly, for I equal to 1 and j equal to 3, nums 1, 0, does not match nums 2, 2, as 1 is not equal to 4. Again, we take the maximum between dp, 0, 3, and dp, 1, 2, leaving dp, 1, 3, as 1. Continuing this process for all I and j, we fill out the DP table step by step. By the end, the table is fully updated, with the bottom right cell, dp, 3, 3, holding the value 2. This value represents the maximum number of uncrossed lines we can draw between nums 1 and nums 2 in this example. Now that we have completed example 1, let's analyze example 2, where nums 1 has 5 elements and nums 2 has 6 elements. We initialize the DP table with dimensions, m plus 1, by n plus 1, filling it with zeros, just as before. This table will help us calculate the maximum number of uncrossed lines dynamically. The initial DP table is entirely filled with zeros, ready for updates as we process the elements of nums 1 and nums 2. The process will follow the same iterative approach, comparing elements of the two arrays, updating the DP table based on matches, and using the maximum function when there are no matches. As we proceed to fill the DP table for example 2, we follow the same methodology as in the first example. We compare each element of nums 1 with each element of nums 2 and update the table accordingly. For instance, nums 1, 0, which is 2, matches nums 2, 2, also 2. Similarly, nums 1, 1, which is 5, matches nums 2, 1, and nums 1, 3, which is 2, matches nums 2, 5. These matches are reflected in the DP table as we increment the values in the appropriate cells. After processing all indices, the final DP table reveals that the maximum number of uncrossed lines, stored in DP 5, 6, is 3. This value represents the solution for this example, showing the optimal alignment of the two arrays without crossing lines. For the third example, nums 1 contains 6 elements, and nums 2 contains 5. By observing the arrays, we can identify 3 key matches: nums 1, 0, matches nums 2, 0, nums 1, 3, matches nums 2, 4, and nums 1, 5, matches nums 2, 3. Using the same dynamic programming approach as before, we construct and fill the DP table. While the exact step-by-step updates are similar to the previous examples, the final result is that the bottom right cell of the table, DP 6, 5, holds the value 3. This indicates that the maximum number of uncrossed lines we can achieve between these two arrays is 3. This concludes our walkthrough of the examples and the DP-based solution for the problem. To understand the time complexity of this solution, we need to analyze each step in detail. First, during the initialization of the DP table, we create a 2D array with dimensions, m plus 1 equals n plus 1, where m is the length of nums 1 and n is the length of nums 2. This involves allocating memory and setting up the structure, which requires m*n time. Next, we focus on filling the DP table. This is done using nested for loops that iterate through all possible I, j pairs, where 1 equals I equals m and 1 equals j equals n. For each pair, the solution performs either a constant time comparison or a max operation, both of which take O1 time. Since there are m*n iterations in total, this step also takes O(m*n) time. Finally, the result is retrieved from the last cell in the DP table, which is an O1 operation. Combining these steps, the dominant factor here is the DP table initialization and filling, giving us an overall time complexity of O(m*n). When we combine all the individual steps, the overall time complexity for this algorithm is O(m*n). Now let's analyze the space complexity. The primary contributor to space usage is the 2D DP table itself. With dimensions m plus 1 and n plus 1, it requires storage for all of its entries. Each entry is a simple integer, which means the total space required is proportional to the table size, resulting in O(m*n) space complexity. Additionally, there are a few auxiliary variables, such as m, n, I, and j, which are used in the loops. These variables each take O1 space and are negligible compared to the DP table. Therefore, the overall space complexity of the algorithm is also O(m*(n). This is a direct result of needing to store all intermediate results for the dynamic programming approach. Let's compare this dynamic programming approach with a brute force solution to highlight its efficiency. A naive method would involve recursively exploring all possible subsequence matches between nums1 and nums2. In the worst case, each element in nums1 would be compared with every subset of nums2, leading to an exponential time complexity of O(2 to the power of m*(2 to the power of n). This is clearly impractical for larger inputs. In contrast, the dynamic programming approach reduces the problem to polynomial time, O(m*(n), by reusing previously computed results and breaking the problem into smaller overlapping subproblems. Additionally, while the current implementation uses a full 2D DP table, it's worth noting that we only need the current row and the previous row to compute the solution. By maintaining just 2 rows instead of the entire table, the space complexity can be optimized to O(n), significantly reducing memory usage while still achieving the same time complexity of O(m*(n). Now let's consider the best, average, and worst cases for this algorithm. In the best case scenario, when nums1 and nums2 are identical, the algorithm still needs to iterate through all m*(n) cells in the DP table to compute the result. Thus, the time complexity remains O(m*(n). On average, approximately half of the comparisons in the DP table might lead to matches or skips, but the algorithm still processes all cells, resulting in the same O(m*(n) time complexity. In the worst case, where there are no matching elements between nums1 and nums2, the algorithm fills the entire DP table without finding any common subsequences. Again, the time complexity remains O(m*(n). The key takeaway is that the time complexity does not vary across different cases because the nested loops always iterate through all cells in the DP table. Mathematically, the dominant factor is the nested loops, which contribute m*(n) iterations, each performing constant time work. This gives the overall time complexity of O(m*(n). Similarly, the space complexity is determined by the size of the DP table, which is also O(m*(n). When tackling this problem, there are a few common mistakes to watch out for. First, it's easy to confuse this problem with the longest increasing subsequence or LIS. However, while LIS focuses on finding an increasing sequence within one array, this problem is about maximizing non-crossing connections between two arrays, which means we need to account for both arrays and their relative ordering. Another frequent mistake is relying on a brute force approach to check all possible pairings between the elements of nums1 and nums2. While this might seem like a straightforward solution, it becomes computationally expensive very quickly, with a time complexity of O(n²). This makes it impractical for larger inputs, such as when the arrays have thousands of elements. A third issue arises when duplicates in the arrays are not handled properly. If you ignore duplicates, you risk either missing optimal connections or making invalid ones, which can lead to incorrect results. Paying attention to these pitfalls is essential for solving this problem effectively. Another important consideration is handling edge cases. For example, what happens if one or both arrays are empty? Or if all elements in nums1 have no valid matches in nums2? These situations can lead to runtime errors or incorrect outputs if not addressed explicitly in your code. Additionally, binary search is a powerful tool for optimizing this problem, but it's also a common source of errors. If the binary search logic is misplaced or implemented incorrectly, it can result in the wrong insertion points, which can completely break the solution. Therefore, it's crucial to test and validate your binary search implementation thoroughly. By being mindful of these edge cases and implementation details, you increase your chances of building a robust and efficient solution. Understanding the context of this problem can also be helpful, especially in an interview setting. The key pattern here is that this problem is essentially a variation of the longest common subsequence, or LCS, but with the added constraint of maintaining the order of connections between two arrays. A good strategy is to start with a brute force solution to get a feel for the problem, and then move on to more optimized solutions like dynamic programming, or even dynamic programming with binary search. It's also important to be able to explain the trade-offs between these approaches, such as why brute force is inefficient and how optimization reduces complexity. Additionally, during interviews, take the opportunity to demonstrate your attention to detail by discussing how you handle edge cases. Finally, remember that the order of elements in the arrays plays a critical role. This insight can help you narrow down the search space and implement more efficient solutions. This problem is closely related to several others, which can provide valuable practice and insights. For instance, LeetCode 300, the longest increasing subsequence, shares a similar concept but focuses on a single array. LeetCode 1143, the longest common subsequence, involves matching elements between two sequences, making it directly relevant. Another related problem is LeetCode 354, the Russian doll envelopes, which also utilizes dynamic programming combined with binary search for optimization. And of course, LeetCode 1035, Uncrossed lines, is essentially the same problem we're discussing, involving non-crossing connections between two arrays. Exploring these related problems can deepen your understanding of the underlying concepts and improve your problem-solving skills. There are several approaches to solving this problem, each with its own trade-offs. The brute force approach involves checking all possible pairings between the elements of nums1 and nums2 while keeping track of valid non-crossing connections. While this method is simple to implement, its n² time complexity makes it infeasible for larger inputs. A more efficient solution is the dynamic programming approach, where you use a 2D DP table to track the maximum number of connections possible for different prefixes of the two arrays. This approach is clearer and more robust, though it still has a quadratic time complexity. For the fastest solution, you can use dynamic programming with binary search. This involves transforming the problem into one of finding the longest increasing subsequence in a specific sequence, and using binary search to optimize the matching process. While this approach is the most efficient with a time complexity of n log n, it requires careful implementation and validation of the binary search logic. Understanding these trade-offs will help you choose the right approach based on the constraints of the problem. Great job! We've wrapped up problem number 1035, Uncrossed lines. Today, we used dynamic programming to solve this interesting optimization challenge. Remember the key insights about dynamic programming and the importance of breaking complex problems into manageable subproblems. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!